Assalamu alaikum and greetings. Our next task says that infinitely long conductor is given with radius A equal 1 centimeter. So here we have our infinitely long conductor where this is with the radius A equals 1 centimeter. And it said if the current density changes as the function of distance from the center of conductor according to law of this 2 times 1 minus r squared divided with a squared. Calculate the intensity of magnetic field on distance r equals 1.5 centimeters from the center of our conductor. Magnetic permeability of copper and conductor, consider it that it's equal. So this is our conductor from copper, and we consider it that these two are approximately equal. What do we have here? Now we know that the current presents the flow of charges in time, and it takes only the complete conductor, all the charges from the complete conductor. But the current density says what is the number of those charges on some small area of surface. Because of that, its unit is ampere per meter square. But what do we have here? In most tasks we have that those charges, that the current is the same through all the surface. It is uniform. The current is uniform through all the surface, and because of that we got in most our tasks that G is a constant, and it can be calculated as we only take complete current of conductor and divide it with the surface. But here in this case that's not like it. What does this say? It says that somewhere here we have more charges, moving charges, than in other areas. It's not uniform. Charges are not uniform. The current is not uniform. Because of that, we have been given what is the function of our current density from the distance of the center of our conductor. And we need to calculate what is the value of magnetic field on a distance r equals 0.5 centimeters. We know that B is equal μ0 times magnetic field, and from here we will get that our magnetic field can be calculated using magnetic flux density. Now the second thing is that we can calculate our B using Ampere's law. We know that B times dl over a closed contour is equal to the μ0 times sum of all currents, or because here we cannot use current, we must use, this is not a constant, we must use the formula that the current actually is calculated with this formula using current density over some surface S, because now our current density changes. So what does our Ampere's law says? Firstly, we must close our contour. We want to calculate, okay, this is a cross section of our conductor. We want to calculate, for example, at this distance, we will call it as an R radius, which is changing. We will get our B and H as a variable from R, from the distance of the center. And then if it said we want for R equals that and that value, we will only put it in the formula and calculate it. So R, this is our closed contour. We need to determine vector B and dl. Well, because the current goes up, it means this is the direction of our magnetic field B and A. And also this is because this is our length of our closed contour. This is dl, which means B and dl angle between them is 0. And we know here we have a dot product of two vectors. This is equal to the intensity of B times intensity of dl times the cosine angle between them, which is cosine 0, which is only 1. So we will write this only as B times dl. But now the next thing which we need to do is also to determine this JDS, current density, and its surface. But what is the current? Also, we have dot product of two vectors, or scalar product, which means we need to determine the direction of G and dl. Direction of G is up, so the direction also of ds, it is normal to this surface. We are analyzing the surface that our closed contour made. Once again, we are analyzing the surface that our closed contour made of this integral. So we choose that it is normal to the surface, and the angle between ds and j is also 1. So the dot product of these two is equal. Now what do? We have integral c b dl equals μ0 times this product is only current density times ds. Our current density is this 2 times 1 minus r squared divided with r squared times ds. Now the question is, what is our ds? What is our infinitely small surface? Well, let's look what is our total surface complete. So our surface is actually a circle. So if we know that the surface of complete circle is r squared times p, the radius, how can we find this infinitely small surface? You can find it using, that is a differential, which means we will find a derivation of our surface. How do we wrote it in math? We say s prime, which is the same as a ds divided with a dr, because r is function radius, which changes. So these two notations are the same, they are telling the same thing, and we simply find derivation of this r square. Derivation is 2 times r times pi. And from here we multiply left and right side with dr, and we will get that our ds is actually 2rp times d. This is one way how can you calculate it. The second way would be, okay, here we have our surface with radius r. What would be infinitely small part of the surface? Well, I would only move for dr, and this length of our circle, which is 2r pi times infinitely small part dr. So this is our ds. You can determine it also that way, or simply using the derivation, knowing the formula for complete surface. So we will write that here. B, we can put it in front of integral. We will get integral of dl. Okay, integral of dl is the total length. But what is our total length? Well, it is the length of a circle. And the length of our closed circle is, because it has radius r, is 2rp, which is equal to the μ0 times 1 minus r squared times ds is 2r pi dr. So what are the borders? From where does our surface start? Well, this is our surface, and it starts from the center where radius r, because that is our variable, is equal to 0, and it ends here at this r. so it is up to R, and when you solve this, you will get that our B is μ0 or test. So now we need to calculate our magnetic field. Here we have that our magnetic field is actually this, B divided with μ0, which means that our magnetic field will have this value. We only erase μ0. And we need, this is magnetic field as a function of distance, radius from the center. And now we can use this formula to calculate what is the value of magnetic field at any point, at any radius, at any distance from the center of this conductor. But our task is to calculate it for R equals 0.5, and when we put that in the formula, we will get that our magnetic field for R equals 0.5 centimeters is 4.375 milliamps per meter. And that would be it for this test. Thank you for watching. See you in the next video.